So hello everyone, my name is Mert Koşan. So I'm a PhD candidate in University of California in Computer Science Department. Today I will present our work AI Decision Systems with Feedback Loop Active Learner. The work was done when I was interning in Visa Research last summer. So there are hot discussions about AI and human decision systems, which one we should select. So the task they can apply is they can decide on the credit card application or insurance application, or they can find some anomaly in the data. So we can ask this queries task to human decider, or we can ask to AI decision system to make predictions. However, these two systems have their own drawback. So if we are working with human decisions, it can be time consuming and the expertise is required. But if we are working with the AI decision systems, there can be multiple label scarcity issues, and the performance, there will be multiple misclassifications because of the gray area problem. Now the question is, should we combine these two methods, AI decision systems and human together? So I want to start with a background example. So let's imagine we have a server machine monitoring system, which is a black box AI decision system. The system monitors 100 server machines, and let's say 5 machines have a weird behavior. So this possible weird behavior can be CPU overload or inconsistent network usage or some malware existence in the servers. So generally in industry, we don't have labels, so we need to apply unsupervised learning to learn this black box model. So there will be no label to verify the real reason behind this weird behavior. So we will have to ask the human to give us a feedback. So we send the queries to human, and human categorize these unsure behaviors and explain the reasons. Then we can store these decisions in our system, the decisions or the feedback from the human, and we can update the server machine monitoring system in the future when it's necessary. However, the big problem here is, even if the human is expertise, they are human, so they have some behavior. So we need to understand the human behavior. Maybe there are different type of expertise of human. We need to ask the correct questions, correct queries to different humans. So how can we make sure that we are asking the correct questions? So to overcome this problem, we additionally add another layer between the AI decision system and the human, which we call it feedback loop active learner. So here, feedback loop active learner actually calculates the relevance score of each query that can be sent to the human based on the human expertise and the behavior. And by getting the feedback, we actually capture two information. One is the human behavior, what is the expertise, what is their interests. And the second thing, we are getting the ground truth, or the reason, explainability of these queries that we can use to update our AI decision system. So this is a general framework of AI system and a human interaction, and in the middle we have a bridging system. So AI decision system decides that given a data, AI decision system will generate some decisions. So I will talk about in detail about our learner, but at the end we send the queries to human and collect the feedback. So for example, we can think of some interaction detector to understand the human behavior as well, but our main focus in this talk will be the middle part, feedback loop active learner. So actually, this problem is a specific problem that there are multiple entities. In the example, there can be multiple server machines. So actually in Visa, we are working with merchants But because of the legality problems, we had to use these applications into the public data set. So I'm not able to give like too much detail about merchants, but this is kind of a similar application. So there are multiple server machines, and each machine generates some multivariate time series data. It can be how the CPU's usage, network usage, and so on. First, we want to represent this time series data in the embedding space with using some pre-trained stream data embedder. Since the stream data embedder training will be complicated, we want to use some pre-trained model, so we will not train during our training. And note that here the input doesn't have to be time series data, it can be graph data as well. So the stream data embedder should be working with, like, you can use some graph embedding methods to pass into embedding space. So in embedding space, you can think if each item, each cross is representing one machine, one entity. So now we need to understand the human behavior, as in the recommendation systems, we need to understand how users are actually behaving. That's why we want to pass from global embedding space to user embedding space. The reason is in global embedding space, we will have multiple groups which can contain the entities having a problem with CPU overload, or network usage inconsistency, or malware existence, but maybe the users are actually care or knowledgeable about only the red sign, the malware existence and network usage consistency, right? So main part of user embedding mapper will map these items into together so that it can be easily classified, and this area can be user expertise area. So now that there is a problem here, this type of data is not really recommendation system. It's not like you can do some pre-survey to understand the human behavior. So because this type of data, like a CPU overload, like some it can be, for example, in Visa, it can be fraud. There can be different type of frauds. You don't really ask people what kind of fraud you are in expertise. So that's why we add additional layer to extract a feature from this embedding space. We hope the layer can solve some cold start problem, or at least easy the problem. So from now on, I will use more technical notations. So here we have each cross represent an embedding of entity I at time t for user A. So we pass this embedding to the feature extractor. So here, if you wanna have some domain specific features, you can use some expert design features such as average distance to all other embeddings. Or you can apply some learned features via neural network. So the good part here is we also have a decision from the generated by the AI decision system. We can also incorporate this as a feature. So the fourth phase of the algorithm will be a recommender that actually calculates the relevance score of each entity for a certain user. That will include the decision from the AI and the feature extracted from the embedding space. Then this recommender will just send top Q relevant item queries to the user, and the user will basically label this Q item with their decision and expertise. Then we will apply, since we can do this operation online learning, we want to use the active learning to train our model. And as I described before, we are only training the last three, and the first one was the embedder, which is already pre-trained. So in our optimization, we use a constructive loss to understand the humans are interested or not. So this is actually classical constructive loss function, but we believe that splitting into different terms can help in different application scenarios. So here we have a RTA, sorted relevance score array, ETA, the binary expertise information from the user, and the hyperparameters. So this looks complicated, but I will give you an example quickly. So we have three terms: L widen, L narrow, and L recover. And so in this example, so this is the relevance score array generated by our algorithm. Higher means more relevant. And we have a budget. So every human has a budget. They will specify a budget that can work on, and their response, or this response can be captured by some interaction detector algorithm as well. So as you can see, they say 1001 and question mark because we don't know their response because we couldn't send the queries because of the budget. So first term is actually working, try to widen the gap between positively ranked true positives and false positives. So 1.5 minus 1.2 and 1.5 minus 1.1. So I'll narrow is looking at another perspective. Misranked true positives, try to narrow the gap between misranked true positives and the false positives. So our main aim is actually pushing this false positives to the end of the list. And since we don't know the items, the relevance of these items to the user, I'll try to get the information, try to capture, maybe there's a true positive serve so we can capture them. So the last term is actually try to recover the unrecommended items. So we conduct, in our experiment, we use a public data set, server machine data sets, which originally have 38 machines with different length of time, measured time with 38 feature. So we want to make the size of the entities larger to make it similar to the data we have used in Visa. So we chunk the data into 100 time series with length of 365. And the classification, the performance is just a machine failure or normally working. So we have three baselines. So we can do some random recommendations or recommendations based on only AI decisions. And we have another active learner mechanism, is a basic random forest, which combines the uncertainty and confidence of these recommendations. So our setting is we use a budget 10 and 20, and evaluation metrics are precision and average precision at Q. And the feedback is the problem. If we don't do real human experiments, how do we simulate feedback? So in this paper, unfortunately, we have only one user to simulate the only ground truth information. But we propose an idea, maybe in the future, we can extend the paper. So basically, as we have a space, we can represent each user in the embedding space with some latent space. We can think of some Gaussian distribution with mean and standard deviation. And the user embedding mapper will try to map the relevant item into this user expertise, the user expertise area. And with this way, we can have multiple users. So in our results, so here each plot in the x-axis represent the number of steps in the active learning. And these are the precision at Q equals to 10 and 20 performance. And our method outperforms the baselines, but more interestingly is our method also converges fast. We don't need around 40, 50 step, it converges. So you need to learn the human behavior as fast as possible, because if you don't learn fast, you will do a lot of mistake in the beginning that can damage to model. We also noticed that the performance with larger queue drops. The reason is, imagine you have only relevant items of 12, but your budget is 20 and you are recommending 20 items, then the precision performance will drop. So the question is, should we optimize the number of recommendation we give, or we use another metric to doesn't actually have a drawback of this, which is actually average precision, which cares about ranking of the recommended items. So in other words, the succeeding 0 will not affect the performance. And here, as you can see, actually the first items are actually the truly recommended, which the performance in both cases are close to 90%. So we also, so here, as you may remember, we are using a human behavior with a different function. So user embedding function, which can actually be costly if we have too many human labelers. We need to learn a different function for each of them. But here, since we have a data, so there's number of data is less, we cannot have a complicated method anyway. So here actually the linear user mapping function performs as much as good as a nonlinear one. And two nonlinear functions actually performs really bad because of the overfitting issue. In the identity one, when we don't use a user embedding, the convergence rate is super bad, which we don't want in this application. So here, quickly I can tell, we also check the sensitivity of the loss or loss function term. And here, when we use all the terms, it has actually reaching the best performance. When we remove the first, which is the widen the gap between the truly ranked and the false positives, and we lose a lot of performance. But the second term and the third term, removing second term and third term is actually similar reduction, but still they're important. But the result shows that actually the most effective term is the first term. So as a contribution, so we highlight the limitation of feedback loop systems. So human AI collaboration may be limited. And we propose a framework for better ground truth generation under understanding human behavior. And we conduct experiments. And for a future work quickly, we want to do some real human experiments to show the effectiveness. We can incorporate or propose user simulation setting, and we want to use a more public data sets to show the effectiveness. The more importantly, now we need to update the original model, but we cannot update every time we get feedback. We need to check when we need to update the original model. Thank you.